This lesson covers the rational function. It's also known as the inverse variation function, but I will most commonly call it the rational function. We're going to talk about the rule, its graph, and the use that we need a rational function for. The rule for a rational function is y is equal to k over x, where k is just some constant number and x and y are coordinates on the graph. It's very important to note that x can never be equal to 0 because you'll notice it's in the denominator. And when you have a 0 in the denominator, it doesn't exist. Also know that the letter K can sometimes be another letter like A or any other letter. Just know that that number or that letter represents a number that is just a constant number 1, 2, 3, 4, 5, etc. What does the rational function look like? Something like this. You'll notice that there are two pieces to this rational function, but in our case, in our math, we only look at what the function looks like in the first quadrant. So that's the only thing that we are going to be focusing on. But FYI, there are two curves in a rational function. The second one, though, in this third quadrant is not what we will be looking at, just the first one. So what is this k? Where do we come from? Where does it come from? Is there a rule or a formula that we use like slope in a linear function? So to introduce k to you, I'm going to give you a table of values like this one. Going up 1, 2, 3, 4 on the x-axis, you'll notice that these numbers here correspond to the x. This shouldn't really do anything for you. Be like, okay, it's a table of values. Is there there's nothing special about it? So I'm going to prompt you and I'm going to say, okay, well, what if we multiplied every x by their partnered y? What would you get if you would multiply the coordinates together? So this is one coordinate, this is a second one, a third one, and a fourth one. What would happen if we multiplied them together? When I multiply them together, if you've already done this or you check here, you'll notice that every single one of these products is equal to 30. If we were to continue this table of values, you would see that all the pairs products would also be equal to 30. So if we were to continue down 4, 5, all the way up to however numbers of x I use, and I multiply them by their partnered y's, you would get 30. The rule for this table of values is y is equal to 30 over x. This is a rational function, and that is how you find your constant k of a rational function. So obviously for a rational function to be true in a table of values, when you multiply your x's and y's together, they should always equal to the same number. Not always 30, just in this case it's 30, but they have to be equal to the same number. So what does the y equals 30x look like? Well, as we pointed out before, it's curving. Here's a curve, right? It's not a straight line like a linear function. It curves downwards. There's no such thing as a slope, really, in a rational function. We don't talk about slope like we do in a linear function. And we are focusing on the first quadrant. So just for fun, I'm going to use a program called GeoGebra just to zoom in a little bit more on this graph so that we could analyze it a little bit more. So here's the curve that I had showed you, y is equal to 30 over x. I'm going to zoom in on the first quadrant, like I had said, the positive quadrant, because that's what we care about. Now, one by one, I'm going to zoom in on the axes. So first thing that I'm going to do is I'm going to zoom in on the x-axis. And if I zoom in, you'll notice that this line gets closer and closer and closer to x is equal to or y is equal to 0, but it's never actually crossing this x-axis. And if I zoom out far, it looks like it is, right? It looks like it's touching the x-axis, but it's actually not. Same for this y-axis. Look at the y-axis. You see how it looks like it's touching the y-axis, but if I zoom in a bit more, you'll notice that it's not actually touching the y-axis. And in fact, a rational function never, ever, ever touches or crosses the axes. It just gets really, really, really close to this. And that's what's special about the rational function. So we actually call these asymptotes. When a function never touches or crosses the axes we call the x and y axes asymptotes. So these are just lines that the function grazes. It just grazes those lines. Now, there are different functions that have different asymptotes. They're not always the x and y axis, but it just so happens that a rational function has an x and y axis that are asymptotes. This also means that our rational function never crosses the origin. 0, 0 is never a point. So just to make it a bit more formal, the definition that I got from Google is a line that continually approaches a given curve but does not meet it at any finite distance. So it never, ever, ever meets that line, or in this case, these lines. So now you know about asymptotes. Let's go back to finding the rule. Right now, you probably know what a linear function y is equal to ax plus b, and we are just being introduced to a rational function. How can you tell the difference between what a linear function and rational function is given a table of values? So I've given you two here, and just take a second and maybe guess or try to come up with a way for you to understand what the difference between a linear and a rational function graph would, or table of values would tell you. And just to get you going, a hint is to remember how to find the constant k in a rational function that I did with you a few slides earlier. I multiplied the x and the y of each coordinate, and I noticed that they got me the same product if it was a rational function. So I'm going to do the same thing here on both these tables of values. And you'll notice something very, very great is that in the first table of values, when I multiply my x and y coordinate together, I get 24 for each of my coordinates. But on this hand, I do not really get the same answers here. I get 4.5, 15, 31.5. They're not the same. These 24s indicate that this is a rational function, whereas this is a linear function. I'm going to give you 4 tables right now, and I would like you to try it yourself and tell me which is a linear and which is a rational function. Do it on your own. I'll give you the answers in a sec. But remember what I had spoken to you about in the last slide where I multiply them together. For the first one, if I multiply them together, I definitely don't get the same product. But what's also an indication is that we have a coordinate 0, 0, which I told you was not possible for a rational function. So this is actually a linear function. For this second table, if I multiply all of my coordinates, x's and y's together, I get 6. So this is a rational function. Down here, multiplying them together, I still get the same answer, so it's a rational function. And finally, if I multiply the numbers over here together, I do not get the same product, so this is a linear function. So one small hint that I mentioned in the last slide, x can never be 0 for a rational function. Just like y can never be 0, x can never ever be 0. I've proven it to you. It does not cross ever 0, 0. And I've also explained it to you earlier that it's because if we have a 0 in our denominator up here, it doesn't work. You would get an error on your calculator, which we all know is not fun. So, for example, if I give you a table of values like this, right away, without even doing any multiplication or any figuring it out, there's a 0 here in the x column. And this is impossible if it's a rational function. So this had to be a linear function in our case because we only know 2 functions, linear and rational. Now let's talk about how graphing. Say you have a table of values or values given to you in the question. The more values that you are given, or the more coordinates that you are given, the more accurate your curve will be. So here is a table of values that I've given to you, and I'm telling you that it is a rational function. The first step is to always plot these points on a Cartesian plane. So I'm going to do that in the next slide. So here I've used the program GeoGebra again, and I have plotted my points on the Cartesian plane, again focusing only on the first quadrant for a rational function. In this case, you'll notice that it might be hard to tell, but you can see a slight curve in these points here. And what you have to do to draw or graph the function is you're going to have to connect these dots as a rational function, remembering to graze the x and y axis, but never actually touch them. And remember, we're not stopping. We're going from infinity to infinity here. So I've done it for you here, again, using GeoGebra. Obviously, the more coordinates you have, the better your curve will look like. So feel free to add coordinates on your own. So here's the table of values that I gave you originally. And if you didn't guess by now, the constant here is 6. So my rule for this table of values is actually 6 over x. So if I wanted to continue just by plotting a little bit more points, I would get 5 in 1.2 and 6 in 1. And that might help me continue my curve a bit better. So I would like you to try it yourself by grabbing some graph paper and plotting the following points in our Cartesian plane. Then see if you can approximate the drawing of the curve. And remember, you cannot touch the axes, you would just have to graze them. So here's a table of values, and I've given you several numbers because I feel like the more coordinates you have, the more accurate your curve will be. So just plot these on a graph paper, making your own Cartesian plane, and see what you get to check on the next slide. When I've plotted my points onto GeoGebra, again, I have a nice curve here that's slightly far away from the 0, but because I've given you small enough numbers, you should just be able to go up by multiples of 1 on our x and y axis, which is what I did here. Just as an added bonus, using the table I gave you to graph, can you tell me what the rule of that line or that function was? And can you continue the table of values by filling the blanks that I've given you here below? So take a second, try it on your own, and then I will give you the answers. The rule for this table is 15 over x. That's my k, my constant, because if I multiply everything together, x times y, x times y, x times y, I get 15. Now here's the tricky part. If x is 10, what is y? So here's my work. If I do 15 divided by my x, which is 10, I get 1.5. So that was easy. The next one is a little bit trickier. I have now the y. It's 1.25, and I'm going to be looking for the x. So I'm going to do a little bit of cross multiplication. So this is what I have if y is 1.25. My x is here. I'm going to cross multiply, and I'm going to get 1.25x is equal to 15, because 15 times an imaginary 1 is just 15. And then at this point, you should know how to solve for x from now is dividing. And you get that x is equal to 12 and y is equal to 1.25. Here's a bit of extra an enrichment, if you will, of approximating a rational function by modeling. So say you were given a Cartesian plane with just random points. Here's a bunch of random points, and you don't know what's going on. But in this case, you know that it's kind of creating a curve. When you're given all of these points, it's actually called a scatter plot, literally like points scattered all over your Cartesian plane, called as a scatter plot. And we do see that it is a curve, but we don't know what the rule is. We're going to look for a pattern by using a table of values. So all I've done here is I've taken all of the points that I saw on the graph in the last slide, and I've put it into a table of values. And then I've said, okay, well, is there a way for me to find a pattern? I know it's irrational. If I multiply them together, what do I get? But you'll notice that I get different values when I multiply them. But I'm sure it's a rational function because it looks like one. So what am I supposed to do if I get different k's, but I am certain that it is a rational function? We're going to find the average or mean of all the multiplied values for k. So of all of those values that I multiplied x and y by, I'm going to average them. So there were 7 products that I found in my table. I'm going to add them all together and divide it by 7. And I get that the average of all of those products was 180. And that's what I'm going to use for my k. So I'm just approximating it. It's approximately y is equal to 180 over x. And to check to see if this is accurate enough, I'm going to look at what it looks like on a Cartesian plane. And in this case, you'll notice that here's my function 180 over x. It goes through some points, not always all of them, but it's pretty close. It's not exactly, but it's a good approximation. And so I can approximate other points on this line using 180 over x. So if I'm given a situation and I need to know what y is when x is 40, I can use this rule to approximate what it would be. Here's your recap page. So we have learned about the rational function. It's also known as an inverse variation, so don't freak out if you see that term. It's the same thing as rational. And the rule for the function is y is equal to k over x. K is found by multiplying the x and y values together, and you should always get the same number in a rational function when you multiply them together, same product. And remember that k is not always k. Sometimes it's a, b, c, d, e, f, g. It doesn't matter. It's just a constant. A rational function looks like a curve, and we only focus on what it looks like in the first quadrant. It never touches or crosses the x or y axes, which means that the x and y axes are called asymptotes. And the function never passes through 0, 0. Remember what I said on the table, x cannot be 0. Makes no sense. Definitely not a rational function if you see x as 0. And lastly, I taught you how to graph a rational function. So to graph one, just plot the points and then draw a curve as best as you can through those points without touching the x and the y axis. And that is the end of the rational function.